Hello, my series on Coarea formula starts with this video. We begin by recalling the amazing Fubini's theorem, which is probably the only way we can actually compute any multivariable integral. What it says is that to integrate a function g that goes from a higher dimensional Euclidean space into R, we can first integrate over vertical slices, and then each x you fix, there is this vertical section, you integrate, you get some value over that, and now you have a function of x that you integrate then over the Rn. So here, pay attention to my picture. You are in Rm, and then you break it up into Rn times Rm minus n. A similar formula is what is called the integration in spherical coordinates, and that again says that to integrate a function, a real valued function on Rn, you can first integrate over the spheres centered at the origin. So this is a sphere of radius r, and because it's n-1 dimensional, you integrate against the n-1 dimensional measure. You can use this surface measure coming from manifold theory, but we just want to use the Hausdorff measure, which agrees with it. And then, of course, you add up as r changes. So I put negative infinity, but in fact, for negative values of r, this is an empty set, and it's just 0, the integral. So it's really 0 to infinity. But you will see why I put it that way. So what do these questions have in common? What do these theorems have in common? What they are saying is that to integrate a function, you can first integrate over a certain foliation of the space. And in these two pictures, the foliations are quite nice and geometric. So the question becomes, for what other foliations does this hold? When can you do this same thing? How nice should your foliations be? And the Coarea formula is a surprising answer to that question. It turns out that all you need is a Lipschitz function, and then the level sets of that function will do. So in these pictures above, the spheres here that we see are level sets, or fibers, we will also call them, of the function that is f of x equal absolute value of x. So for a fixed r, the pre-image of the single point r is the set of x's where f of x equals r is just a sphere. So what integration in spherical coordinates is saying is that you can integrate over fibers of this f first. In this other picture, the foliation, if we write xy for a point in Rm, where x comes from Rn and y comes from Rm minus n, I may have misspoken there, this equals x, so this just projection map. And these blue sets are just pre-images of the function f. So the Coarea formula says if you have a Lipschitz function from a larger dimensional space, Euclidean space, into a lower dimensional one, then for almost, well, we have to be precise, for Ln, almost every value in the target space, the level set f inverse of the singleton z is h m minus n rectifiable. Okay, so in the previous pictures, these pre-images were nice m minus n dimensional manifolds. So this is a generalization of that. And so we will talk, of course, a lot about this concept. What it gives us in this setting is that you can actually integrate over this set. That's all it's giving me. So for every z, f inverse of z is some object that I can integrate over with respect to m minus n dimensional Hausdorff measures. So, and then you play around with z. As z changes, these level sets foliate your space. You should always go back to your Fubini and the spherical coordinate setting. So what does it mean as you change z? So that means integrate with respect to z as z changes over the target space Rn. So this is the same as it was in the Fubini and spherical integration case. So is this equal to the integral of g over Rm? The answer is almost. It cannot be, because you can take f to be, say, the constant function. And so there's no way we can have this equality, dLm. However, if you introduce a correcting factor, a kind of Jacobian, then it does hold. So remember from the area formula story that if f is Lipschitz, then it has a derivative almost everywhere. So this Coarea factor Cn of that derivative, which is a linear map from Rm into Rn, is defined to be the determinant of the square matrix dfx times dfx transpose. And then you take square root. So that is the Coarea formula. That's our theorem. There is a lot to be unpacked here. Just thinking about crazy Lipschitz functions makes you wonder, is this really true? And once you convince yourself of the validity of this, and once we will see the proofs of this, you will hopefully come to appreciate how deep this theorem is. Again, if you take certain f, like this projection or the absolute value of x, it gives us the Fubini's theorem and spherical integration in spherical coordinates. Okay, there are some remarks to be made here, some immediate ones. It could be that for some values of z, the level set is empty. If no value has mapped to z, then this preimage will be 0. So if this preimage is empty, then integral over that thing is set to be 0. And that's actually will be one of the nice cases. The other point is that even if f is C infinity, f inverse of z does not have to be a smooth m minus n dimensional submanifold for all z. One obvious example is again the constant function f, which is definitely C infinity. You see that for almost all z, the level set is actually empty, which is a good case, by the way. But for one particular value of z, the preimage is all of our m, so it's definitely not m minus n dimensional. But you can play around with this constant function. You can have two huge pieces of your Rm, two open subsets, where your function is constant, and then there is some smooth way of connecting them. So you can create a lot of crazy functions. So what else is there? The proof for C infinity or C1 functions is not necessarily easier. Partly because of this previous remark that it's not the case that if you have better regularity for f, the foliations are nicer necessarily. So we'd rather prove it for Lipschitz than for arbitrary, for more regular functions. In fact, for spherical integration formula, we need Lipschitz because this function absolute value of x is not C1. At the origin, there's the problem. Okay, let me show you some pictures of what can happen with foliations. So here I have my function f that goes from let me do a little trick here so I can annotate on this. So my function f, let me see. Okay, finally the details. So my function f, hopefully if I can get it to right, f, okay, so goes from, probably better than nothing. This is an app that is supposed to help me write on web pages. Okay, so f goes from R2 into R. What is this? And that function is given up here. And when you fix A in R, the picture you will see in here will be my fiber preimage. So this will be F inverse of the set Z. Sorry for this. This was working before. But that's all you need here. So notice that this function I have is a polynomial. It's C infinity, it's analytic, it's the nicest that it could be. But look what happens with the fiber. So I'm at this value A equal this much. And here are my fibers. They are nice one-dimensional manifolds, 2 minus 1, until something happens. At these values, you see that this is still a one-dimensional manifold, but disconnected with two pieces. But there is a very particular value of A where you have this one manifold piece plus a single point a little bit farther away. And that single point stops this set from being a one-dimensional manifold. So even if for this nice smooth polynomial, there is some point where it is not a manifold, but wait for it because there is another A value for which this is not a manifold, and that happens at A equals 0. So when A equals 0, again, this is not a one-dimensional manifold, a famous homework in any manifold book. And once you pass to positive values of A, still this is this goes back to being a one-dimensional manifold. Now, if you put absolute value around this function and you play around, you can see much crazier pictures. So that just illustrates this remark that even for C infinity functions, it is not guaranteed that every preimage will be a nice manifold of the right dimension. So what is the plan for the series on Coarea formula that I have in mind? So we are going to see the proofs of all the claims that have been made here. So we will see proof of rectifiability of preimages, almost every preimage. We will see some linear algebra to justify the particular definition of this Coarea factor. We will see a weak version of Sard's theorem. This Sard theorem will take care of the cases where the rank of the derivative of function is not n, the maximum possible. And then we will see implicit function theorem, which will turn the Coarea to Fubini's theorem. So we will deduce the Coarea formula from Fubini's theorem by applying implicit function theorem. The idea is already in the spherical integration coordinates. So here, if you zoom in around a point away from the origin, this is what the foliations of your domain look like. So the fibers come, of course, from parallel, let's say parallel spheres. And what implicit function theorem will do, it will kind of iron out these fibers into really vertical ones. If I can draw a vertical line. Okay, how many do I have? 5. So after you apply the implicit function theorem, via a C1 diffeomorphism, you will turn the picture into this picture. And now integrating over fibers is just doing Fubini. That will be the core idea behind the proof in the regular part of the set, and then the Sard's theorem will take care of the critical part. So that all is going to come up in future videos. Make sure you subscribe and you turn on the bell so that you are notified as the videos get uploaded. It's important that you follow them in the order they come. Finally, a couple of references. So this proof is, this Coarea formula is due to Federer. So his book has the proof, of course. The other book where you can read this from is, again, Evans and Garip's book. The title is Measure Theory and Fine Properties of Functions. And if you Google, you will find some nice notes by Nicola Escu. I hope I spell it the right way and I pronounce it the right way. And these are very beautiful notes, about 19 pages. And the good thing about them is it starts with the simplest cases of the Coarea formula, for example, for linear maps, and then for C1 maps, and then builds up gradually from there until it reaches actually the full generality, which is for functions from rectifiable domains into rectifiable targets. And depending on your need for the Coarea formula, you can read as much as you wish from those notes. So give me some thumbs up if you like this video, and let me know what you would like to see during these proofs, how deep you want me to go, how detailed you want me to go, if you want more pictures, less pictures, and whatnot. So until I see you in the next video, where I will talk about what tools we will need in the proof, and and an overview of the proof in the general bird's eye view point of view, then see you in that video. Thanks a lot and have a great day.